sponsored by Chicago White Metal Die Casting. A few housekeeping items that we'll get to before we begin. Just a reminder, I think you should have been alerted to the fact when you logged in that all the attendees their phones are muted. That's to help kind of keep the background noise down. So just wanted you to know, in case you're trying to say something and you're not able to get through, that's why. So all the phones are muted. Next item, there could be a few second delay from when I change the screen to when it changes at your end, depending on internet speeds and that type of thing. So just wanted to give you a heads up if I start going to a different slide and talking where you don't have that up on your screen. Just give it a minute or hopefully 2 or 3 seconds, and it'll catch up. One other thing, as you go through the seminar or the webinar, keep in mind if this information seems to be valuable for you and you're interested in having a similar type of seminar at your facility, please let us know. It would be something that I do on a very regular basis for companies. It's usually handled through a lunch and learn series type event at a company location. Let you bring in as many people as you want. I have a big box of samples that makes it nice to go through, and we can look at different things that different industries are doing and die casting on real life samples, which is kind of nice. The seminar can be customized for a specific need that you might have. If you want to talk more about surface treatments, we can customize it toward that. So keep that in mind. If that's something you'd be interested in, please let us know, and we can help coordinate that with you. Okay, we'll go ahead and begin. Again, I am Jody Scollard. I am the sales manager for the Southeast U.S. So anybody joining us from the Southeast, if you have a new project or application that comes up, I'm your guy. So you'll see my shining face at some point maybe. I've been with Chicago White Metal for 5 years, just over 5 years. I was with another die cast company for 3 years before that. And then prior to entering the die casting life, I was a mechanical engineer, program manager for a tier 1 automotive company. So that's kind of who I am. On the phone also are a group of panelists from Chicago White Metal. These guys are going to be answering your questions real time via the online chat that we'll get to in a second. John Miller, Mike Dimitrov, and Tom Rock are available to answer your questions during the presentation. Your questions are definitely welcome. The way we're going to do that, because it's such a large group we're having today, it's going to be a little tough to do this verbally. So there's a question section of the control panel that's on your screen right now, and we highlight it here. So if you could enter your question in the space provided and hit send, and you will get a response. If we don't get to everybody's question right now, and you have questions that come up later or after the presentation is over, I have some contact information for myself that I'll give out a little later, and you're more than welcome to call me, email me, whatever, and I'll help you out as best I can. Okay, for the agenda, this is the items that we're going to talk about. The webinar provides more of a general overview of the die casting process and industry. We don't get too specific in any one area or topic. If you need more information about a specific area after the webinar is over, again, please don't hesitate to contact me and let us know, and we'll try to get you whatever we can. My goal through this is to have you, if you could just think about the projects either that you have in production right now or that might be on your drawing board. Think about it in the light of die casting. Maybe it's an option, and if so, we'd be happy to work on it with you. So we'll talk a little bit about why die casting, what are the areas that we think die casting offers an advantage. We'll look at the various alloy options that are available. We'll talk about the processing of die casting. You hear in the industry a lot about hot chamber versus cold chamber, and we go through that and talk about what the differences are, what the advantages, disadvantages are of them. Die casting economics, we show material prices and how that relates to the various alloys that are out there, and then also some other costs that go into to making up a die cast overall price. We'll look at some design strategies and tips. We look at some fairly basic ones, but they're ones that we look at when we get a brand new project in from a customer. There's some things that we initially look at, and it would be good to talk about those, and maybe you can look at those at your end as well. We go through a MAGMA analysis, demonstration, and case study. We'll talk about the various prototyping options that are available with die casting. We'll show a tooling plan and features and options that are available for tooling. And then we'll talk about the various post-casting and secondary operations that are available. There are literally dozens of things that can be done to a die casting after the actual casting is completed, so we'll talk about some of those. So if you look at why die casting, there are a wide variety of alloys available. The three main families of alloys that we talk about are aluminum, magnesium, and zinc. There are various alloys within each family that we'll look at a little bit, but those are the main three. There are other metals that can be die cast, but those are the ones that are overwhelmingly most common in the industry, so we'll talk about those. They have a good range of physical and material properties. We'll look at some of those. We have links at the end of the seminar or webinar where we give some literature and documents about more specifics of the physical and material properties that we'll give you. Die castings produce a net shape or as close as possible component. That's one of the biggest benefits of die casting versus other type of castings, investment castings, sand castings, permanent mold, those type of things. The goal for a die casting is to give you right out of the tool as close to possible as the shape of the part and dimensions and tolerances as you're going to need. The little we can touch the part after it comes out of the casting, the better economically it's going to be for you. A single die casting can replace multi-part assemblies. Another great reason to look at a die casting if you have some sort of steel part or other assembly that has fittings on it that we can convert to a single part die casting. That is obviously a cost save all around and makes a nice part. Die castings have very good thin wall capabilities. Those capabilities vary a little bit from alloy to alloy, but we talk about those here coming up. The as-cast surface finish of die castings is very good. Obviously, there are dozens and dozens of finishing options available if the as-cast surface is not what you're looking for, but as it comes out of the tool, it does have a nice finish. Die castings give the best part price of any of the casting processes, which is another one of the main reasons to look at a die casting. Because of the part coming out of the tool, net shape or as close as possible, there's very little secondary processing on many applications, and it gives the best part price. In fact, it's a good option for projects with as little as 500 pieces a year volume. I know that seems counterintuitive for people when they hear about die casting, but there are situations where converting something to a die casting might be a cost save even at 500 pieces a year. If we look at the various material selections and alloys available, like I said, there are basically three families of metals that we talk about. Aluminum alloys. We highlight here aluminum 380, which is the one that Chicago White Metal works with, but there are numerous others in the aluminum family. 380 is the most common of all the aluminum alloys that are used in die casting, so we focus on that one. Aluminum has very light weight, has excellent strength properties, excellent thermal and electrical properties. Many people use these aluminum 380 for heat sinks and that type of application. And it is the lowest cost per unit of volume. We talk about cost here in a little bit, but when you look at the price per pound of aluminum and its weight, it becomes right now the best cost per unit volume alloy. Magnesium. The magnesium alloy we have highlighted here is AZ91D. There are other alloys that are available, but this again is the alloy that Chicago White Metal uses. It is the lightest weight of all the die casting alloys. Magnesium is. It's about 2/3 the weight of aluminum, so it's about 1/3 lighter than aluminum. It's a similar weight to most of the common plastics, so many people would look at converting things from plastic to magnesium if they need a little extra strength that they can't get out of their plastic and don't want to have any increase or weight or much increase in weight to convert over. Magnesium is a great option. It also has excellent EMI properties. So if there are electrical components inside of a application or device, magnesium is a great option to help keep the noise away from your electronics. The zinc family of alloys, we highlight here zinc number 3. Some people will also hear these referred to as Zamac. That's a kind of a trade name of the zinc family of alloys. You'll hear Zamac 3, 5, 7. We highlight number 3. We also use another couple of those alloys, but number 3 is kind of the most used of the alloys. Zinc is the heaviest of all the die-cast alloys. It's about 2.5 times that of aluminum. So you can see it's a pretty heavy alloy to use. One of the things you can do with zinc is typically have thinner wall sections than some of the other alloys. So you can compensate for that weight disadvantage with zinc by designing in thinner walls, and it helps with the weight disadvantage of zinc. Zinc also is very, very strong. Highest strength of any of the die-cast alloys that we talk about. ZA8 is another kind of a spin-off of zinc alloys. The 8 refers to 8% aluminum content that is in that alloy. It's processed very, very similar to the zinc family, but the higher aluminum content does allow it to have a little bit higher strength than the zinc families. And is, like I said, is processed similar. Also on this table, if you look at part size range, and we talk about this coming up in a little bit, but these are specific to Chicago White Metal. Based on our tonnage size of machines, this is the size limit that we're able to achieve. Other die-cast companies can do different things based on the size machines they have, but this is us. So we talk about this at the end when we look at Chicago White Metal capabilities specifically, but I just wanted to highlight that this is specific to us. Again, you see the machine tonnage range that is here. That is specific to Chicago White Metal, and we talk about that in a little bit. The expected die life is an interesting thing to talk about. People always ask, how many shots can I get out of my tool? And it varies by the alloy that's going to be run. We use aluminum as kind of a baseline, which is why we have the 1X shown there. So if, let's just use a number, 100,000 shots that aluminum tool can shoot before seeing some things on the parts that are going to require some tool modifications or refurbishment. That number may be higher or lower based on the application and cosmetics required, but if you just use 100,000 as an example, magnesium, you should be able to get about 3 to 5 times that than aluminum with the magnesium dies. Zinc, we give it a life of a part kind of guarantee. Zinc is very, very easy on tools and the corrosion of tools, and so zinc is very, very has a very long life. ZA8, because the aluminum content is a little less than the straight zinc, so it gets to the 2 to 3 times amount for a ZA8. This chart is kind of breaks down the various material properties of the alloys that we talked about. This specific chart will be available to you, so please don't think you have to memorize everything that's on the screen. We will, again, send out a link at the end of the presentation that'll have this exact chart in there. So it'll give you all the different strength characteristics. You can see the densities of each alloy and how they compare. So that'll all be there. Okay, Next, let's talk about the cold chamber versus hot chamber processing of die castings. Again, you hear these terms thrown around in the industry, so it'd be good to understand what they are, what the differences are. When we refer to high pressure, or when we refer to die casting in North America, that really relates back to the high pressure die casting process. And it differentiates itself from other types of castings like sand casting and permanent mold and investment, where those processes have the alloy being poured by gravity. It's not under pressure. In our process, in the high pressure die casting process, the metal pressures can get up to about 20,000 psi. So when we inject the metal into the die, it's extremely high pressure, and that's what allows us to get the thin walls and the features as cast in net shape as we can. So that's kind of why that lends itself. The two processes we talk about are cold chamber and hot chamber. We have a little animated clip coming up that'll show this in motion, and you can see a little bit different about the differences. The hot chamber process is used for the lower melt temperature metals, so zinc, ZA8, lead, which we don't cast, but is there, and small to medium magnesium parts. Those are hot chamber applications. Cold chamber are for the higher melt temp metals, such as aluminum, brass, and the larger. We use that for larger magnesium parts. So here you can see an example or a pictorial, I guess, of the cold chamber process. Conceptually, it's pretty easy. You have a amount of, in this case, aluminum or magnesium for a cold chamber outside the machine. A ladle goes in and scoops a given amount of metal in, pours it into the plunger area, and then is shoved into the die at very high pressure. So conceptually, it's pretty easy to understand how die castings work. There are many other factors that go into it, but as you can see, the metal goes in, part solidifies in the tool opens up, spits out a part, and is either ejected into a water bath or is extracted and air dried on a conveyor. Again, cold chamber die casting is for the aluminum, larger magnesium, and the ZA family of alloys that have the higher aluminum content, the 12 and 27% aluminum. Some of the advantages: it allows us to process larger, more complex parts in this process. It allows for higher metal pressures, which gives an improved quality when we have heavier wall section parts, usually in the larger aluminum parts, as well as pressure-sensitive applications. There are times when an application will need to be leak tight or have an internal pressure, and the cold chamber process is an advantage for that. Some of the disadvantages: there is a greater chance of entrapping air during the shot, and it's typically a slower cycle time versus hot chamber. So it adds to goes into the economics of the process. Here you can see the hot chamber animation. Again, it's very similar. The biggest difference between hot chamber and cold chamber is how the metal is physically injected into the die. In this view, you can see the injection system being represented here is physically inside the molten metal. So the metal is never exposed to the atmosphere as it is injected into the die. The lower temperature alloys, such as zinc and magnesium, can run this way because it's not as aggressive on the injection system, and is why it's buried inside there. But the rest of the process, from the tooling and how the part cycles in the tool is the same. The biggest difference is, like I said, how the metal is physically brought from the molten area to the tool. So hot chamber die casting, again, it's for the lower melt alloys. So the AZ91 magnesium, the zinc family of alloys, as well as the ZA8, which is the 8% aluminum alloy. So it's not doesn't have enough aluminum to push it to the cold chamber. Some of the advantages: we're able to control the metal temperature better, improve filling capability of the thin wall castings, reduce porosity because of the way that it enters the tool and able to fill the thin wall. We're able to control porosity better. And as I mentioned before, it's typically a faster cycle time than the cold chamber, which helps with the process costs. Some of the disadvantages: the gooseneck that you saw in the animation, which is how the metal, or the mechanism from which the metal gets into the die. That system is a little more expensive than the cold chamber setup, but not significantly. And there's no intensification stage in the shot, so we're not quite able to get as much as high pressures as it goes in. Some of the price factors that go into making a die casting. These are what go into it when we build a quote for a customer. Obviously, metal costs. Each alloy that we talk about has a different price per pound that fluctuates throughout the year. We show a snapshot of that coming up in a slide next. The processing costs, the labor amount goes into it. The size machine that we're running a die casting in will add into the overall cost. The various cycle times for a component. Some of the larger parts with thicker walls and that type of thing might have a significantly longer cycle time than a smaller application. The number of cavities that go into the tool. If it makes sense to put 2, 4, or more cavities into a die, we can obviously do that, and that can save on the processing costs, as well as automation options. The casting process is relatively automated, and we try to maximize that as much as we can. The post-processing costs, again, are varied. The part comes out of the die and goes down a conveyor, and then has to get the gates and runner system trimmed off in a secondary operation, so that factors in. And then the various finishing that's available. Vibe finishing, polishing, it really depends on the application and what type of cosmetic results you're trying to achieve, what the application is, if it needs to be impregnated, if the part needs to be impregnated because of a leak tight concern, or needs to pass a leak test, that might factor in. So there's various amounts that go into it. Tooling costs, obviously, is part of the factors into all this as well. The number of cavities that we put in affects the tooling costs, as well as any side actions or slides to form various features of the part will affect the tooling costs as well. This slide shows the material costs, and again, this is a snapshot of, I don't know, a couple weeks ago, relatively up to date. But again, this fluctuates during the year. But we show the larger bar is the actual cost per pound of the alloy itself. So for magnesium, right now the cost is about $2.25 per pound. Aluminum is about $1.25 in that area, and zinc is about $1.05. So that means something, but it doesn't mean as much as if when you factor in the cost per cubic inch or the cost per unit volume. So that's why we show a second bar in here that shows when you factor in the density and actual weight of the alloy, how that comes out. And with the metal prices as they are right now, aluminum is slightly better than magnesium for cost per cubic inch, as you can see by the two bars, and then zinc is significantly higher cost per cubic inch because of, as we mentioned, the weight of zinc is about 2.5 times that of aluminum. So there are things we try to do to factor that out. Like I mentioned, if we can design out some of the wall thicknesses to make them thinner, that will help with the zinc cost per cubic inch part of it. So now if we go through a few case studies of projects we've worked on in the past with customers to show the benefits of die casting. In this picture, you can see a manifold type part. It started life as a aluminum and brass assembly. So you can see where the aluminum, there we go, the aluminum part would have been, and then 5 or so different fittings that were brazed in place. So it was a pretty costly assembly for this customer. When we worked with them, we tried to see if we could convert this over to a single piece zinc die casting, and that's what we ended up doing. All the threads that you see here are as cast. There's most likely a small flat area that we have to include in order for the part to get a gate there. Maybe not on some of these, but typically we'll put a flat in an area so we can gate into the thread. But external threads are an option, and that allowed us to make this part as a single piece die casting. Obviously, it was a huge cost save for the customer, saved about 85%, and the payback on their tool was very, very fast. This next component was a printer. It is a printer cartridge, printer carriage component that started out as a plastic piece with some threaded inserts that were molded in. The customer indicated that the overall strength of the part was not exactly what they needed, but they didn't want to sacrifice very much weight in the overall product by converting to something. So magnesium was a great choice for this. It gave them the strength they need. The weight did not change that much. They could remove all the different brass and steel little inserts that you can see in the plastic part, and allowed a good cost saving as well there. This next conversion case study, these are very, very small air chuck screw machine brass parts that were converted over to what we call mini zinc die casting. There's kind of a different, a whole separate process surrounding the mini zinc process. These components are run in extremely small, extremely fast die cast machines. In fact, these parts probably run something in the 20 to 30 cycles per minute range, so very, very fast. So these things are spitting out almost like popcorn out of the machine. So it's a great option for parts that are small. Obviously, these parts have to be small to run in these machines, and there's a lot of conversion activity if you're screw machining brass like these parts were, or steel or other things that can be converted to zinc. And there's usually a very significant cost save to do that. In this case, the annual savings on these parts were about $85,000, so very significant. This next application is a microwave splitter. It is a very low volume requirement part. It started life as a machine from solid, which you can imagine with all these internal features and different things going on. That was a challenge and very, very costly to do this as a machine part. Converting it to a die casting, even though it required several pretty complex slides to form some of the features and some post-casting machining to touch up some of the features, it still was a significant cost savings over machining from solid, and allowed the customer to see a payback on their tooling investment in very, very fast order, even though it was a small quantity that they needed per year. This next project, you can see it's a handheld or shoulder-mounted video camera. This highlights the number of components that were used in this application. There were 11 die-cast parts that were used. You can see the non-coated parts in here. The more structural parts are aluminum, and the majority of the exterior parts are magnesium. Most of the parts, or 5 of the parts, were cast net shape, so there were no other secondaries required on those. Some of the other parts received some drilling and tapping, but for the most part, as they came out of the die, was good enough. The outside components that are magnesium were mostly spec'd that way because of the EMI shielding that were required for this application, and that the magnesium did a great job of providing that. Okay, if we look at some of the die-cast tips or design tips that we would recommend, again, these are things that we look at when we first get a project, and they may seem a little simple, but they actually can factor in have a big impact on the price and quality of the part. The first thing we look at when we get a new project in is are there areas that we can remove some of the mass of the material. You see in this diagram on the right, there's a boss that comes in, and then there's a heavy wall section that's underneath the boss. Heavy sections are areas where porosity may creep in. It also adds unnecessary weight, which is cost into the part. It causes us to have a slower cycle time in the tool, which again factors into the cost. So if there's any areas that we can recommend a customer, take out weight or do some things to reduce some of the overall weight of the part, it's a big advantage all around. Die castings don't necessarily have to have a consistent wall thickness throughout the entire part, like plastics or other things are recommended to be. But it's still a good policy. If that can be done, that's great. It leads to a little better metal flow and some other features that are characteristics that are an advantage. Again, in this slide, we try to ask a customer to use ribs wherever possible instead of maybe a heavy mass area. Ribs do a couple things. They help metal flow from one section of the part to the other. They also increase the strength of the part as it comes out of the die and in application. So ribbing is a good thing for die castings wherever possible. Fillets and corners, again, that seems like a simple thing, but you'd be surprised how many times we get an application that has very sharp corners or very little radii and corners, and that's bad on a couple of levels. First, it could create stress points on a component and lead to premature failures. The biggest thing for us is that being able to have generous radii in the corners allows the metal to flow better. When liquid metal goes in and tries to fill a cavity and solidify, it does not like to try to do that around a sharp corner. So anywhere there can be radii factored in is the best. Draft is another thing that we'll look at when we first get a new project in. Draft is going to be required on pretty much every feature that we need in a die casting. What happens is when, as the part solidifies, the metal will shrink toward the inside of the part and onto a tool. So we will need some draft on the features in order to get the tool apart and to eject it from the die. Interior features need about 2 times the draft of exterior features. So as a general rule, we'll ask for about 2 degrees of draft per side on the interior features of a part and maybe 1 degree on an external feature. Obviously, more the better for us to properly get the tool apart. Sometimes limited on what a customer can do from a draft standpoint, in which we understand, but we do request as much as you can give us. There are areas or times where drafts may be minimized or even eliminated. Those are kind of special cases, but there are times when that's something that needs to be done. Prototyping strategies, another common question we get is, how do you prototype a die casting? Obviously, people don't want to spend the investment on a brand new tool in order to just get some prototypes. So what are the other options that are available? We can do a single cavity hard tool. What we mean by that is, if there's going to be in production, say a large 4-cavity die in production, maybe we make a very small single cavity die instead in order to get some prototype or maybe even some pre-production parts off of it. We can also do a single cavity soft tool. We can utilize a tool steel that's not hardened up to what we would use in production, and that's typically good for, say, a couple thousand parts, maybe a little less depending on the application. Rubber plaster molding is another great option that we suggest to people when you need maybe 10 to a couple hundred parts. That's a fantastic option. There are companies out there that we work with and recommend for that process. There's machining from wrought and sheet stock. This is usually done for a smaller quantity. If you just need a couple of parts to touch and feel and show around, then that's a very good option. And we're also looking for new rapid prototyping techniques. There's always new things coming up, and so we try to stay on top of the new things out there. If we consider what the tooling construction cycle is as we get a new project in and we are working with a customer, once we get the final model from a customer, we'll construct it's a rapid prototype called an FDM, Fused Deposition Model. It's a machine we have in our engineering facility in Chicago, and it's great to be able to just make something very fast, be able to show to the various departments that are going to be touching the part, show to outside vendors if necessary of what the part's going to look like. It's very helpful. We'll then perform a design review with the customer, go back and forth on tolerances and anything that might be able to be changed or modified to help the part or solve some issues that we can solve ahead of time. Then we go through a MagnaSoft flow simulation on every new project. In a minute, we'll show you a case study of MagnaSoft and what the advantages we see of this. Again, we do this on every new project. It's not something that's typical in the die-cast industry for them to do, other die-casters to do on every project, but it is something that we find extremely valuable and recommend for every new project. Once that is all complete, we'll subcontract a tool maker. We do not build dies in-house, but we've got a fleet of people that we utilize to build our dies, both domestically and offshore. We'll then do a tool design review with the customer to make sure that they're happy with how the tool is designed. It's your tool, so we want to make sure you're happy about it. Make sure where all the parting lines are going to be located and the gates are located is in ejector points or in areas that are satisfactory to you and to the application. We'll then build the tool and sample the tool, and then once that is completed, we will finish up or construct the trim die. As I mentioned, every part will get trimmed off as a secondary option, trimmed off the gates and runners, and we usually wait till we get a real-life sample to complete that. It usually makes a lot of sense. Some of the various tooling options that are available, we can do a self-contained die. These are usually for larger parts, where we'll build a die base and the cavities dedicated to one specific project. If the part is small enough, we'll consider or we'll try to put it into a small unit die where we have existing die bases and unit holders that we utilize that are common. So you're not having to pay for the entire mold base if your part is very small, and we can fit it into a small unit die. So it's a way to save on tool cost. There are times when we'll do family tooling, meaning we'll put 2 or more similar type of parts into one die. And like I mentioned, multi-cavity tooling whenever the annual volume and application warrants it. Here is a blow-up of the die that we were showing a minute ago, just to show some of the features. You can see at the bottom here where the metal flows into the part. It then flows across the part, and then out here. There's some overflows on this area, and then the runner system goes out to a vacuum assist system. So we're forcing in the metal at very high pressures. We're pulling at the other end with vacuum to try to get as much air out as possible. That obviously internal porosity is a big thing that is desired to be controlled. So we do whatever we can to do that. Trying to see what else is on here. The tool steel that we use is a H13, which is gives us the maximum die life and machine performance that we can achieve. Here's a blow up of the part that is created by this die, this fictitious die. And you can see some of the features that we've already talked about, but that can be incorporated into a part. This part has got fins on this end, so it's utilized as a heat sink. In some cases, people utilize fins on a die casting instead of having to do a separate component with fins for a heat sink application. You can see some of the very thin walls that are achieved on this part. All of these exterior holes that you see, we attempt to get those as cast, depending on the size and functionality. We'll try our best to get them as cast instead of having to go in as a separate secondary operation. Any type of indications such as part numbers and logos and that type of thing are easy enough to put in the tool ahead of time, so those can be those can show up on your part as well. Okay, next we'll step through a MagnaSoft case study. Again, as I mentioned, once we get a new project in, we'll work with the customer to go through this MagnaSoft project or analysis with them. Kind of a real quick flow chart. We get the part in. We'll go through the MagnaSoft analysis that we're about to show you. It's an iterative process. We'll go back with the customer and based on the results of the MagnaSoft, try to see if some design improvements or modifications can be done on anything that shows up as potentially an issue. This could take a day. This could take a week. You just don't know what the analysis is going to show. And then once everybody is satisfied and in agreement, we'll go through the tooling initiation. Here's the part that we're talking about the case study for. It's a fairly small part, 4 by 4 by about 5 inches tall. During the design review with the customer, it was indicated that there's an area of this part that has a leak-free requirement or a pressure tightness requirement, as you can see by the red arrows. So that was indicated during discussions. During the first run, after about 10 minutes of the analysis, you can see there were some large, thick sections in this part that is going to, this is a solidification time chart. So you can see where this area that's red and yellow is going to take a lot longer to solidify in the tool than the blue and bluish green areas. Unfortunately, in this case, it goes right through, or is located right where the bore will go right through for the pressure tightness. So that is that was a problem. Another view of the part from above, and you can see again the thermal gradients that are in there based on the thick wall sections. The thermal gradients, the uneven thermal gradients leads to distortion. And then that distortion can lead to stresses that are remaining in the part after it comes out. So the things that we did to work with the customer to try to redesign and improve on the design, as you can see in this slide, there's some metal taken out in a couple different areas. You can see this section on the left where my pointer is, that was completely solid, and then we came back in later after the analysis was completed and put a long slide in there that took a good bit of material out, as well as a slide from this direction which took another big chunk out. The other thing we did was where the bore for the pressure tightness was going to be positioned, instead of machining that completely out, we cored out the majority of that first in the die, which was a big advantage. So when you see the results in this slide, no longer do you have the bright yellow and red areas. It's a much more even solidification picture. So the parts are, the entire part is solidifying fairly consistently. The next slide shows what we do after we got the design completed and finalized. The MagnaSoft software helps us identify the best way to gate the part. As you can see, the metal's flowing in and then gets split off in a few different areas to help fill. And then once the metal gets all the way to the other end, it gets pushed out these little small overflow areas that are here. So all the entrapped air and other undesirable things that happen during the shot are pushed out to the end. In addition, the MagnaSoft helps us identify where the cooling lines are going to be located and optimizes for that for the different areas of the part. If there's some areas that are thicker or require more cooling, then the system helps us identify that. So in conclusion, obviously initially we saw the issue with the pressure tightness requirement in that area. The complete analysis fit inside the 2-week engineering and design lead time frame that we typically give for a MagnaSoft process. And the first castings right out of the chute were good and have had no defects to date. So as you can see, it's a very, very powerful tool that we utilize, and which is why we try to do it on every project. It's a huge advantage being able to identify things up front instead of having to wait till the tooling is completed. We'll talk quickly about some of the post-casting operations that are done. Again, there are literally dozens of different things that can be done on a die casting after it comes out of the tool. Various deburring, machining if required, both conventional and CNC, various types of coatings and platings and paintings. We can put graphics by pad printing and silk screening on them, as well as do any type of mechanical assembly if a customer requires some clips or springs or gaskets and other type of things installed on a die casting before it gets provided to them. We're more than happy to do that. The various surface treatments that are available, we don't go too deep into what is available in this webinar. We're looking to, well, first we'll provide you some technical data sheets after the webinar is completed that will have details on other options that are available for surface treatments. In addition, we're looking to potentially have a separate webinar just on surface treatments. I know that's a very hot topic for a lot of the people attending, and we're looking into that. Obviously, surface treatments provide a decorative finish based on whatever the cosmetic requirements are, as well as providing a protective barrier for the different levels of protection that are required. Some applications are fine as cast. The application does not need any coating, but majority of parts do get some sort of coating. And again, we'll provide some other information to you. For surface treatments, the best thing to do is really give us a call. We'll kind of step through what's available. We'll look at the application with you and see what you're trying to get out of a part, what the cosmetic requirements are, what the corrosion protection requirements are, and we can really work with you with providing samples and other options that that'll get you something that you need. Okay, now we'll take a few minutes and just look at Chicago White Metal Casting specific capabilities. We've been in business since 1937. We're a private family-owned company. Here are the major markets that we serve. These are not all of them, but the top ones. We do about 22% medical and dental applications. We do transportation at a lower tier level, kind of tier 2, tier 3. We do telecom, consumer recreational, defense, and then that covers about 55% of the business. It really spreads out from there as far as other industries that we support, lawn and garden, kind of you name it. There's probably parts that we make for it. From an existing client base aspect, we have about 300 active customers right now with about 600 different active parts. So you can see it's a pretty large amount. Our largest customer is less than 15% of our total revenue of about $30 million. So we try to keep it as evenly spread out as we can and not get too much involved with one specific customer for obvious reasons. Some of the registrations that we have, we are ISO 9001 registered since 1995. We are also ITAR registered for any military projects that require it. We are ISO 14000 registered. We're the first American die caster to achieve that. We're also working with the EPA on a couple of their performance track programs. This slide is a little similar to one we saw earlier, but it gives a little better breakdown of the machines that we have and part sizes. You can see in aluminum we have 10 machines up to about 800 ton, 11 machines in magnesium, 6 in zinc, and the ZA8 alloys, and then we have external sources for the multi-slides zinc, the real small process parts that we talked about. From a machining standpoint, we have 28 machining centers in-house in Chicago. We can do obviously both machining of the die castings as they come out of the die, as well as potentially support you if you have a project where it's just going to be machining. It's not a die cast application, but you have a production level machining need that we might be able to support with you. We also can support prototypes in our machining department. If there's a project you have a prototype need that makes sense doing it as a machine part, we can work on that with you as well. Also, from a contract assembly standpoint, I mentioned if a customer comes to us and they say, hey, you're making a die casting for us, but we've also got these other components that it might make sense to come in with that already pre-assembled. We're more than happy to do that. We work with all types of different mechanical components. We don't do really any electronics assembly, but really anything mechanical we can help you out with. Finishing options, again, we talked about that, but not in depth, but there are dozens and dozens of different options, from deburring and blasting and different options. Again, pad print and silkscreen graphics, as well as some other operations that we can work on. So toward the end here, why Chicago White Metal? We feel that we're not necessarily a die cast company that also machines or plates, that type of thing. We feel like we have competency that spans all of them. So we feel that from a product design standpoint, where we can help our customers work through the design process that includes up to creating 3D models of your part. If that's something you'd like for us to perform for you, we can do. Obviously, the die casting, machining, CNC and conventional machining, the various coatings that we work with and can help with, and the assembly. So we feel that all those are our key features and capabilities, and that's what stands us apart. Very good customer support that we have for everybody. Again, we've been in business for almost 75 years now, so we have experience for quite a while. And most of our management team sits on the various industry committees, NADCA, the North America Die Casting Association, and the International Magnesium Association. We sit on various groups with. Again, that is as we get toward the end of our webinar, we mentioned several of the documents and literature that we will be sending out links to shortly after the webinar completes in a couple of minutes. I also invite you to visit our website. We have a very, very nice library of documents and literature, technical articles. It's very extensive, actually, so please go on and see that. After the webinar completes, we're going to close the question session. So again, if you have any questions after this or have an application you'd like for us to take a look at, whatever, feel free to contact me. You see my office number and an email address on there. This information will also be going out in the email that's coming out shortly, so you'll have it on there as well. Again, we want to thank you very, very much for your time. We hope the information is useful for you. And as I mentioned before, one more time, if this is something that you would be interested in having at your facility, please let us know. We'd be more than happy to schedule that with you. Again, thank you very much.